In this session, we'll solve some numericals on the armature reaction. Before solving the numericals, what are the remedies for the armature reaction that we'll look into in brief, then we'll move to the numericals. The armature reaction remedies are the brushes must be shifted to new position of MNA so that when there is armature reaction there is a shifting of the MNA. Therefore, brush axis should be shifted along the MNA. Then the most popular method is they are incorporating in the machines. There are extra turns in the field winding which is very easy to compensate the demagnetizing ampere turns. These slots are made on the tips to increase the reluctance to avoid the armature reaction. The laminated core of the tissues are staggered also for reduction in the armature reaction. In big machines, there are some windings, they are placed in the pole shows, they are connected in series with the armature so that they are producing the flux in such a direction that they are exactly opposing the flux produced by the armature conductors oppose the armature flux automatically. Therefore, for neutralizing the demagnetizing effect of armature reaction, an extra number of turns may be put upon each machine on each pole. Therefore, the number of extra turns per pole can be calculated if the F is the field current and if lead angle is given in electrical degrees that we see in the later case it should be converted into mechanical. But first, what is the number of extra turns per pole required? That is equal to it is you have to nullify the demagnetizing ampere turns and the number of extra turns required is ATD divided by IF is the extra number of turns which are required on the field winding so that they are nullifying the demagnetizing effect. In that IF is the field current. Then to convert the electrical degrees into mechanical degree, that is what you have to do is the electrical degree divided by the number of pairs of poles. That what we are getting here is the conversion of the electrical degree into the mechanical degree. Then we'll look into the numericals. The first numerical, a 4-pole generator with a wave connected winding with 722 conductors and it is delivering 100 amperes at full load and also brush shift is given as a degree. Calculate armature demagnetizing and cross magnetizing ampere turns per pole. It is very simple, straightforward. The numerical, just you have to list out the data given. That is the total current is given delivered is 100 amperes is given. Is not talking about any field current, therefore take it as this 100 ampere itself is the total armature current. Then the based on the wave connected or a lap connected, you have to find out the current per conductor. Current per conductor. That is the current which is flowing in each armature conductor. That you are getting from the total armature current divided by the number of parallel paths. Here it is a wave connected, therefore current which is flowing in each conductor is Ia by 2, that is Ia by A, therefore Ia by 2 that is equal to 50 amperes. Z is given, P is given, theta that is M, what I have mentioned here is it is in terms of mechanical degrees, that is a degree. Okay. Now he asks you to find out ATD and ATC per pole. Just you have to write the equation. ATD per pole is theta M divided by 360 multiplied by Zi. At the same time, ATC per pole is Zi into bracket 1 by 2p minus theta M by 360. All the data are given. Just you have to substitute in this equation. That is theta M is 8 that you are substituting here. 360, Z is 722, I is the current which is flowing in each conductor, that is 50. Then what we are getting is 802 is the ampere turns for the each pole which is having the demagnetizing effect. Then similarly we can find out the cross magnetizing ampere turns per pole, that is 722 into 50, that is Z and I. You have to put Z is 722, I is 50, then 1 by 2p, p is the 4, therefore it is 2 into 4, it is theta m is 8, 360, that is if we are working out, we are getting 3710 is the cross magnetizing ampere turns. These are very simple numericals on the armature reaction. And we will look into the second problem. A 250 kilowatt 400 volt 6 pole DC generator has 720 lap-wound conductors. It gives a brush lead of 2.5 degree mechanical from the geometrical neutral. Calculate the cross and demagnetizing ampere turns per pole. Neglect the sent field current. Here he is not given the total armature current, but he is given the data for output current, that is a load current. How to find out the load current? The output power we know, that is in the case of the DC, the power P is equal to V into I. Therefore, I is equal to P divided by V. Therefore, it is 250 into 10 raised to 3 divided by 400. That gives the current I. IA, that is the total IL. But in this case, no sent field current is mentioned about anything about the sent field current. Therefore, IL is equal to IA, that is equal to 250 into 10 raised to 3 divided by 400, and the rest of the data are directly given. Therefore, IL is equal to IA because he is not mentioned about anything about the field current. It is 250 into 10 raised to 3 divided by 400. Therefore, we are getting 625 amperes is the total armature current. Therefore, what I am interested is current per conductor. It is a DC generator has lap-wound generator. Lap-wound generator. Therefore, I is equal to I divided by number of parallel poles. In the case of lap, it is number of parallel paths is equal to number of poles. Therefore, it is I divided by P. Therefore, we are getting 104.2 amperes is the current in each conductor. Z is also given as 720, P is equal to 6. Then theta is given to 0.5 degrees. Just you have to make use of the same formulas here also. Substitute the values of theta m, that is theta m is 2.5 divided by 360, z is 720, I is 104.2, that you have to substitute. What you are getting is 521 ampere turns. Is the demagnetizing ampere turns per pole. Similarly, you have to substitute for cross magnetizing ampere turns, that is what we are getting is 5731 ampere turns. Okay. Then the third numerical, that is very simple and straightforward. Calculate the demagnetizing ampere turns. He asked only to calculate the demagnetizing ampere turns, but to read the numerical properly and accordingly you have to solve. He asked you to find out only demagnetizing ampere turns. He is given the number of poles, lap-wound is 720 conductors, 720 turns is given. Just you have to look into very carefully here. Giving 50 amperes if the brush lead is 10 degree mechanical is given. Just you have to look into Z. You have to calculate Z. Okay. There is a little bit of a twist is given here. Lap-wound generated with 720 turns is given the number of turns, not the number of conductors. Giving 50 amperes lead if the brush lead is 10 degree mechanical. Just have to very carefully you have to do this numerical. Okay, I is given. Z is 720 into 2, not 720, now it is 720 into 2, because he is given the number of turns. To calculate the number of conductors, what you have to do is you have to multiply net I am connecting to here the number of conductors is 720 into 2 because he is given number of turns. Therefore, conductors is equal to number of turns multiplied by 2. Therefore, we are getting the 1440 conductors we are getting. That we have to substitute. Okay, but very carefully do this. Okay, therefore, I have got the equation as ATD per pole is equal to theta m by 360 into Zi. Here it is 10 divided by 360. Here you have to multiply 720 I am taken. Here it is 2. Here we have to multiply 2. Then what I am getting is the 500. Okay. That is the number of conductors is what? The number of conductors is 2 here. That is what you are getting is 250 into 2. That is, it is not 250, it is 500 ampere turns is the demagnetizing ampere turns what we are getting here. Okay, this is all. But very careful what the data is given. The look into the data and you have to the substitute the values. So that we are getting 500 ampere turns. Okay. The next numerical a 6-pole generator has an armature current of 150 amperes. The wave connected 480 conductors. Is asking to find out the demagnetizing and cross magnetizing ampere turns of pole at full load if the brushes are at GNA. If the brush is shifted from GNA by 5 degree electrical, brushes are shifted from GNA by 5 degree mechanical. Here the only thing is that everything is given for 3 different value of theta. He asks you to find out demagnetizing and cross magnetizing ampere turns. Here brushes are at an GNA means theta is equal to 0. Brushes are shifted from GNA by 5 degree electrical. This you have to convert into the mechanical, that is 5 divided by number of pairs of poles. Here 5 divided by 3 pairs of poles, it is 5 divided by 3 degree mechanical you have to put in the equation. In the third one it is straightforward, theta is equal to 5 degree, you have to substitute directly and you have to find out the answer. A very simple numerical here. Therefore I am listing out the data here. The current per conductor is 150 divided by P. Here the wave connected, it is a wave connected divided by 2. Therefore I am getting 75 amperes. The number of conductors Z is equal to 480. The number of conductors here is equal to 480 is given. The number of poles is 6. Okay. Then the theta mechanical, you have to, in the equation you have to put theta in mechanical degrees. Therefore theta electrical degree divided by number of pairs of poles, then it is what we are getting is in terms of the mechanical degree. Then for a different value of theta you have to find out ATD and ATC. The first case is theta m is equal to 0 because brushes are at the GNA means geometrical neutral axis means it is theta is equal to 0. Theta m is 5 degree electrical here, that you have to convert into mechanical by 5 by 3 in the second case because he is given 5 degree electrical. In the third case you have to theta is equal to 5 degree directly, it is a mechanical, you directly can substitute. These are the fundamental equations for calculating ATD and ATC per pole. The first case I am putting theta m is equal to 0, then ATD and ATC is equal to 0. It is quite evident, that is if there is no armature reaction, there is no shift of a magnetic neutral axis. Therefore, theta is becomes 0. As such, there is no cross magnetism and demagnetizing effect when the theta is equal to 0. When theta m is equal to 5 degree electrical, that is equal to 5 by 3 mechanical, in that case we are getting ATD as 167, ATC as 2833. 2833. And for theta m is equal to 5 degree, the mechanical, what we are getting is 500 and 2500 as a demagnetizing and cross magnetic ampere turns per pole respectively. So we have to calculate the numerical. In the last numerical, we have to find out the extra sent field turns necessary to neutralize the demagnetizing effect. That is, you have to find out the extra turns which is required to nullify the demagnetizing effect. How we are getting it is ATD divided by IF is the equation for the extra number of turns. Therefore, you have to find out first ATD, then you have to find out the extra number of turns required to compensate ATD. First, here he is given one more twist in this, as generator supplies a current of 143 amperes, means supplying to the load. Then apart from that, there is a 10 amperes is the field current. Therefore, in the case of shunt machine, the total armature current is load current plus armature current, that is 143 plus 10, that is 153 amperes is the current which is the total current here. That is, you have to make it as ampere. Okay, that's the current is in terms of amperes. Therefore, it can Z is also given, P is also given, theta m is also given. Just you have to find out first ATD. ATD is theta m by 360. Theta m is 10, that is a 10 degree mechanical is given. 360, Z is 492 and I is 153 by 2 because it is wave connected. That is what it is, 153 by 2 is per current per conductor. That is what I am getting is 1046 ampere turns is the demagnetizing ampere turns. So it is for wave connected. Then for both is asked, and cross magnetizing, demagnetizing for if it is a lap connected, what we are getting the same equation. However, here it is 153 divided by the number of poles is 4 here. That is what we are getting is 523 amperes. Then what is the extra turns required for wave connected? That is ATD divided by the field current. ATD divided by field current, that is 105 approximately. In the case of the lap connected winding, external shunt field requires are 523 divided by 10, that is equal to approximately it is 52 number of extra turns are required to nullify the demagnetizing effect.